Welcome back. So now we are ready to go to lecture 4 on this series for density functional theory. And we are going to wrap up the Hartree-Fock theory that we have done so far. In my opinion, we need to go through the Hartree-Fock theory in order to understand what's going on with density functional theory. And that's what we've been doing so far. The good news is the operators that we are dealing with, so the energy terms of the Hamiltonian, are common, of course, to the Hartree-Fock theory and the density functional theory, which are both theories that actually have one goal, is to solve the Schrödinger equation for molecules and for solids. So today we are going to get a promotion from 1 electron and 2 electrons and move to many electrons. So what have we done so far? What we've done so far is that we focused on the wave function quantum mechanics. So when you look at the interpretation of quantum mechanics as solving the time-independent Schrödinger equation, we look for a wave function. And in Hartree-Fock, and at least we've seen this for both 1 and 2 electron situations, we formulate the solution in terms of atomic orbitals. So what we mean by atomic orbitals, let me remind you, because it's a key concept, these are the solution of the non-interacting electron, so electron not interacting with other electrons, but an electron interacting with an ion. That allows us to generate trial wave function that we use in the variational principle, and we try to find those wave functions that minimize the energy. So what we are missing, of course, is the correlation. In fact, in Hartree-Fock, as I introduced last time, and I will introduce again, I will repeat today, correlation is basically the mistake we make. This is actually the error we make when we use those formulation in terms of atomic orbitals. I'm going to try to explain that again today because it's a central aspect. And everything is based on the variational principle. So at least the Hartree-Fock approach allows us to get an upper bound for the energy, because of course we know that the right solution will have a lower energy, since the variational principle tells us that the solution of the problem corresponds to the lowest energy. Okay, now for 1 and 2 electrons, we need to make sure that the wave function is normalized, simply because we want to make sure that the total probability of finding an electron anywhere in space is indeed 1. So that's something that's quite obvious from a physical perspective. But mathematically, we have to impose that. So now if we have n electrons, each of them has 3 spatial coordinates and 1 spin coordinate per electron, that gives us 4 degrees of freedom per electron. So we can write, if we write x as a combination of the position r and the spin sigma for each atom indexed by the index I, we can then put this in the normalization equation that's given here on this slide. That basically tells us that if we look all over the space, the probability of finding the electrons is 1. So we, of course, need to perform the integration over the x values, which incorporate both the position and as well as the spin. Now we can also come up with the electron density. Of course, it's going to be the central variable that we are going to consider more and more as we move forward in this DFT course. And that density is obtained by this equation there. So you will notice in that formulation that as opposed to what we've done before, in the previous equation on the previous slide, we do not integrate over every single degrees of freedom. We integrate over all of them, but 1, if you will, so position and spin, and that are going to allow us to get a function which is just of 4 variables, so the position and the spin, for instance. So the density is actually very useful, because the density is going to give us the probability density of finding an electron in a region, in a certain minimum region around a certain point. So this is actually very attractive, because intuitively we can actually understand what density is. In fact, the concept of density predates density functional theory or quantum mechanics. This is something we can actually measure or intuitively imagine. This is not so for wave functions. When you have a wave function of 3n or 4n degrees of freedom, and if n is like the Avogadro number, there's absolutely no way to develop an intuition for that. Nobody, the human brain is not equipped to visualize that kind of thing. The density is more intuitive. In fact, it can be measured. For example, in STM, just like this famous quantum coral from the IBM group, which showed that basically trapping an electron wave function inside a coral made out of iron atoms that show in red here on this picture. And of course, the iron atom there were moved by an STM tip. So this is something we can see and we can interpret. Of course, if the wave function is normalized, the integration of the density is now going to be equal to the total number of electron n. So the n value comes from the fact that on the previous slide, I actually put an n in front of the integral to calculate the density. So you can go back if you missed that. Now, we have this is one of the constraints in finding the solution to the Schrödinger equation, is that the wave function is to be normalized. There is another constraint that which I already introduced last time for 2 electrons, is the Pauli exclusion principle. So the Pauli exclusion principle basically means that 2 electrons cannot occupy the same state. And mathematically, it is exactly equivalent to saying that for an electron, like a fermion, we have the wave function has to be anti-symmetric upon exchange of two particles. So let's say that I take these 2 particles xi and xj. If I exchange them like this, I must include a minus sign. That's really what it means. So just to tell you, of course, since the electrons are indistinguishable, what you observe, if you observe electron, it makes no difference, because of course what you actually can measure is the square modulus of the wave function. So the minus sign does not matter. But in the math and in the solution of the Schrödinger equation, it does matter. In fact, we are going to see explicitly one example of that. So fermion cannot occupy the same state. But this is in contrast with bosons, and in fact, we're not going to talk about bosons in this course, but just for your interest, of course, bosons are described by a principle in which the wave function upon exchange of 2 particles does not change sign. As a result, 2 bosons can occupy the same state. And for example, in this experiment there that I show a schematic on the bottom right, together with Pauli's picture, we can see that bosons actually occupy less space since they can occupy the same state. Okay, so we have those 2 constraints on normalization of the wave function and the anti-symmetric nature of the wave function due to Pauli exclusion principle. By the way, I'm going to insist on this, and I'll talk about Pauli exclusion principle a little bit more, because this is actually one of the strengths of Hartree-Fock theory, that it actually can do that. It actually also corresponds to an energy term. So it actually corresponds to an energy term from our expectation values, and we are going to see an example of that in this screencast. So we end up with this problem here. This is the time-independent Schrödinger equation. We've spent at least 3 lectures introducing what the kinetic energy T, the electron-electron interaction V, and the interaction with the external potential Vx are. Just as a reminder, those operators, we have the kinetic energy, we have the interaction with external ions, and then we have the interaction between the electrons, which is Coulombic in this case. Okay. Further, we know that how to solve this equation. We have basically a procedure, and the procedure is the variational principle that says that the correct answer, so what we call the ground state, the ground state, which is phi, which is the state in which the electron will be the electrons will be at the lowest energy. So that ground state is obtained by minimizing the expectation value of the Hamiltonian, which I wrote here as a sum of the three corresponding terms. So we need to do that, but we also need to do that with the constraint of normalized wave function as anti-symmetric wave functions. Okay, this is important. So let's go back. Let's try to think a little bit what we have done so far. So now in Hartree-Fock, really the specificity of Hartree-Fock is that you're looking for a solution. So the trial wave function for the variational principle are obtained as a product of the of atomic orbitals. So basically, solution of the electrons, each electrons not interacting with one another. So we suppose that by using that as a trial wave function, we might be close to the right solution. That's the idea. And it's an intuitive picture, of course. We say that the electrons mostly behave like as if they were not interacting with one another. And then we make a correction in the energy. And then we obtain something that looks like an upper bound for the energy. So for the two electron system, we've done that, the product of atomic orbitals. And of course, we need to ensure the anti-symmetry. So for example, in the blue box there, the anti-symmetry is not taken into account, but we need to do that. What we did for two electrons, we did not worry too much about, we worried about it, but it turns out that we put the antisymmetric nature of the solution in the spin. So the spin part of the solution was anti-symmetric. The real space part was symmetric. So a symmetric solution times an anti-symmetric solution, of course, it's anti-symmetric. Okay, so let's review that again, because it's really crucial. And if you understand that for two electrons, you will understand that for many electrons. So for a single electron, of course, we can just do a product. There is no problem with the anti-symmetric nature since we have only one electron, so there is no such thing as exchanging them. For two electrons, we have a product of solution, and here I separated the spatial part, psi, and the spin part, chi. And once again, in this case, this solution here, it's indeed a product of atomic orbital, but it is not anti-symmetric. So we need to anti-symmetrize this to obey Pauli's principle. And we, for example, have this solution here, which is exactly the one we looked at last week. So in last lecture, where the spin part is anti-symmetric and the real space part is symmetric. Therefore, the total wave function is anti-symmetric, which is a good trial wave function since it obeys the constraint. For those of you interested in quantum computing and quantum information technology, it turns out that the spin part is actually an example of an entangled state. It's a state that it's actually what happens from quantum mechanics. It's a state that if you observe, let's say you have two electrons here, if you observe one electron to be in spin up, you will know for sure that the second one is in spin down. And so this goes back to an entangled state. It means that the two electrons are actually entangled. The spin of one, if you know the spin of one, the spin of the other one is imposed. That's what it means. Now, what we need to do a big leap from two electrons to many electrons. So we have to think about the two constraints. So normalizing the wave function is not too complicated. We just can normalize it just by integrating it and just dividing by the integral if it's not one. And but for the constraint of symmetricity, we have to think about a mathematical device that will allow us to build a solution which is going to be anti-symmetric upon exchange. Basically, it's going to be an object that when we exchange two particles or two states, the sign will change. And of course, in linear algebra, we have the perfect tool for that. It's called a determinant. And in fact, it's very well known as being the Slater determinant, which actually obtained by building a trial wave function this way. So in the red box, this is the determinant obtained from the independent solution for each particles. For each particle. So that's very nice because indeed, if you invert two rows or two columns, you're changing the sign, which is exactly what the anti-symmetric condition tells us. So that's nice. By the way, this solution is not, it's actually not normalized, but that's fine. We can normalize this. All right. So we have the Pauli principle, which is automatically obeyed. Now you may wonder a little bit of my notation. I sometimes for the many-electron solution, I use psi, like here, or I use phi. Okay, so if you actually look at the Hamiltonian, in general, we are looking for a solution which is a phi. So you may think it's just a notation. It is a notation, but it's a convention. It's a convention we use. So that's something I would like to show you here. When the electrons we allow the solution to be an interacting solution for the wave function, then we use phi. But when we are like in Hartree-Fock, we use psi. So when you use psi, we do that explicitly to say that the solution that we try is really built from orbitals. So basically from solution of single electrons that are not interacting. So in other words, we have to use psi, like in the second equation, in green for the Hartree-Fock, and again, this is what we obtain. So now, when we do this, of course, we have different terms of this. We have the non-interacting kinetic energy. Why is it not interacting? Well, because we are calculating the expectation value for a non-interacting solution. We have the last term, which is the external potential. And then we also calculate the Coulomb interaction for the single Slater determinant in red. So it is sometimes confusing to students because I'm mixing interacting and non-interacting. So what is this about? Okay, we do include an interaction VEE, but what we don't do, we don't allow, we force the solution psi to actually be a product of non-interacting particles. That's what we mean by non-interacting particles. But we actually correct the energy for the electron-electron interaction. That's what it means. We are going to spend quite a bit of time in the rest of the screencast looking just at that. Now, one thing that's actually a defining property of Hartree-Fock theory is that this electron-electron interaction, so this expectation value here in the red box, is actually the sum of two terms, which we are going to look at in an example in the next slide. The first term, the U term, is actually the Hartree potential. So this is the interaction of an electron with the average solution, the average presence of an electron somewhere else. The second part is the exchange energy. Now, this is a very important distinction here because it may be a little bit too formal for you now, but it's normal because I'm going to show you in an example next. But the first term, U, is actually a classical term. Is the interaction of an electron with a sea of electron, if you will, which is classical. The second term, there is no classical equivalent to the second term. This energy EX is an energy that comes solely from the fact that we are imposing the solution to be anti-symmetric. So I'd just like to really make sure that you understand this. And the best way to understand is to actually look at an example. So let's go back to our 2 electrons solution. So I can use this in all generality. I can write this where the spin and the positions are just embedded inside the solution. So we have indeed a completely anti-symmetric solution here, but I did not separate the spin and the spatial part in this equation. It is normalized properly. It's 1 over square root 2. And so the idea is to calculate this expectation value of the electron-electron operator, and we obtain it this way. Just so as an aside here, I use phi. I could have used psi since these are non-interacting particles. So the convention I told you, I did not actually obey it here. But in any case, this is a good place for you to pause the screencast and to convince yourself that if you calculate its expectation value for the trial wave function that I have on the top of this slide, you obtain 2 terms. And it comes from the fact that you have the antisymmetric wave function. So you will have the first term and you have the second term. The first term is actually a classical term. And let me explain to you why. Here, I suppose that we apply this to molecules, so the solution can be real. Therefore, I didn't put a psi1 star or anything, but don't let this distract you. The point is that in the yellow box, we have psi1 times psi1, so psi1 square, and psi2 times psi2, both at the same position. So it's psi2 square. Psi1 square is the density of electron at 1 and at R1, and psi2 square of R2 is the density of electron at R2. So basically that first term is nothing else than the interaction between two clouds of electron. So this is a classical term. This is Hartree potential. Okay, so that's easy to understand, that one. The second one, there's no such a thing. It's a much more complicated one. Actually, it looks the same, but it's not, because I can no longer do those square. And remember, the psi1 square, psi2 square, I can no longer that because they are on different position, evaluated at different position. So there is no classical equivalent. So I was talking to you at the beginning of this screencast, I was talking to you about this intuitive idea of densities. In this case, we cannot really write densities here. But that terms comes solely from the fact that we have an antisymmetric wave function. So I actually invite you to, again, pause the screencast and try to calculate this expectation value without imposing the Pauli exclusion principle. And if you just use a solution like psi1 R1 times psi2 R2, which is indeed a product of atomic orbital, but which is not antisymmetric, if you do that, you will only see the classical term. You will lose the exchange term. The reason why I insist on this is that this is a mathematical manifestation on the energy of your system of the Pauli exclusion principle. So the Pauli exclusion principle is not just about imposing Hund's rule when you fill state with arrows up and down like you've done before, you've done for many years. It does also change the energy. And this is why it is so crucial in the variational principle, because it's going to provide an energy term due to the exchange. So that justifies why we write the expectation value as this sum of the two terms, the first one being classical, so the Hartree contribution, and the second one being what's called the exchange integral, so the fact that you impose the exchange principle. That's also the contribution of Fock in this. That's why it's also sometimes called the Fock integral. And we obtain this here. And again, we cannot, here I rewrote it by actually using complex states. That's the same thing as we did before in slightly different notation, just so you are familiar with the different notations that exist. There's no classical equivalent to this. Okay, so that's a purely Pauli exclusion principle effect, and it's necessary. Now, one big question that students ask: then what's wrong? What's the problem? It looks like we are doing pretty well here. We are solving the problem. We have a recipe to find to try to find the ground state using the variational principle. We understand how to impose the constraints. It's all nice. Not quite, because the only approximation really that we make in Hartree-Fock is to impose that the solution is a product or is made up of solution of independent particle. And this is something that usually requires a little bit of thinking for students to understand what it means. So I'm going to provide you a couple of intuitive pictures of that in the rest of the screencast. But I'm going to start with some kind of a artistic picture to try to make you understand what's going on. So imagine for a second that you have an electron, which is shown here by the cloud in the gray cloud in the center. That suppose you have an electron that's very localized. If that electron is very localized and is of course negative charge, the probability of finding another electron close by is going to be diminished, simply because the fact that the electron is there will reduce the probability of finding the electrons around it. So that's actually shown here by a hole around the electron. But in my trial wave function that I used, I cannot account for that. Why? Because the solution of the electrons are independent. So the other solution, the other electrons do not care that this electron is localized. It is not built in the solution. The solution is simply going to be obtained by a combination of independent particles. So even though we do include the interaction between the electrons, that interaction is obviously larger than it should be, right? Because the electron would like to be farther away from each other, therefore minimizing the energy. But we do not allow the electrons to do that because they are treated as independent in the solution. So I hope it helps. There will be another, not visual, but another picture based from probability theory to try to explain that a little bit further. So that's what basically I'm saying. We are missing the correlation. The fact that if an electron is somewhere, the other electron has to be the probability of finding the electron close by is lowered because of they are both negative. So we are missing the correlation, and you may think that it's a small effect. And in fact, if you look at the total energies, the mistake you make is not that large. In fact, relative to the total energy is a fraction of a percent, a small fraction of a percent. So you may think, it's not such a big deal. Well, unfortunately, it is a big deal because that energy, as small as it is enough to really be responsible for all the quantum physics that happens in materials and molecules. So that's actually what differentiates a system from being classical plus exchange and being fully quantum mechanical. So even though that's strong, that's weak, the effect can be very strong. So that's also one of the reasons why DFT was developed, because we realized that that was not something we could live with. Now let me give you another interpretation for those who are not yet convinced of what the limitation of Hartree-Fock is. Let's look at another example, and this one is going to be I'm going to borrow it from probability theory. So forget about electrons for a second. Okay, forget completely about electrons. Suppose that we have two events A and B, and I'm going to call them. I'm going to use something that I came up on the fly during the live lectures. For those who have taken the live lecture, I'm going to say A is the probability that somebody is listening to music very loud in their dorm at night. And B is going to be the probability that another student, you, for example, that you can sleep tight during the night, right? So A is the probability that one student makes a lot of noise. B is the probability that you can sleep tight. Now, if the two events are independent, for example, if the person who makes noise lives 3 miles away from you, the fact that you can sleep and the person making noise those two events are totally independent. You are not going to be influenced. Your sleeping pattern is not going to be influenced by the noise of the other person, and the noise of the other person is not going to be influenced by you sleeping tight. So in probability theory, that's basically saying that the two events are independent, and therefore the probability of the two events happening at the same time is just the probability of one times the probability of the second one. I think that's pretty clear. Now, imagine that the person who is making noise, so A, lives on the floor above you in your dorm. The probability of you sleeping tight and if the other person is making a lot of noise, they are definitely not independent. They are dependent events. So now the probability of you sleeping tight and the other person making a lot of noise is actually going to be they are going to be correlated, and you can no longer do that as a product of the two events, but you are going to have to use this Bayesian statistics, which is basically you read that equation at the bottom, for example, as so the last part, for example, of the equation on the bottom right would be the probability of you sleeping tight times the probability of noise of having noise if you are sleeping tight. So the if is important. So in other words, those elements are correlated. Okay, this is exactly the same idea of correlation as we see in electrons. Now that's the same thing for electrons. If the electrons are close by, okay, the probability density of finding them are going to be influenced. So the probability of finding an electron at a given place depends upon the probability of finding the electron, let's say, close by. Now, if the two electrons are far away and do not interact much, you could imagine that the two probability are independent. And so therefore you could get away with the first solution, which is just the product of independent event, just like we do in Hartree-Fock. Now, the big problem with this is that unfortunately, Coulombic interaction is very slowly decaying. So the interaction between two negative charges extend very far in space. Therefore, the first equation, so the validity of Hartree-Fock is never really fully justified. So this is what we are missing when we look at a Hartree-Fock solution. Okay, I hope this is clear. You may have to replay this a little bit until you convince yourself, or maybe come up with your own interpretation. Now, the correlation in correlation, definition of correlation just for two electrons is basically the error we make in Hartree-Fock. This is the simplest definition in all quantum chemistry. Correlation is what we are missing. That's basically what it is. So let me show you some data that we have for a number of elements that we have here, where we have many electrons. Of course, the correlation for hydrogen is zero because, well, guess what? The electrons are, there's no electron, there's only one electron, so there's no way to interact with another electron. And you see that the correlation energy, it actually is smaller and smaller. I mean, the part of the correlation energy is bigger and bigger, but relative to the total energy is smaller and smaller. Look, for example, for rhenium, it's just minus 6 eV for a total of 23,000 eV. So the relative error you make is very small. Unfortunately, as I said, it is small, but it's crucial. So that's the mistake you make. So basically, something that anybody should be able to say by the end of this course is that to say this, what's in the next title, there is no correlation in Hartree-Fock by definition. Now, people, of course, were not necessarily happy with this. And historically, people have tried to improve that, and actually very successfully, should I say, especially for molecules. So the idea was that Hartree-Fock, with all its, I don't want to sound like I'm actually saying Hartree-Fock is bad. It's not. Historically, it's actually very important, but it's actually pretty smart. I mean, everything that's done in Hartree-Fock was pretty elegant, I think, and very nice. And on top of that, it's not that far from the real solution. So when we have a solution that's not far from the real solution, you can use that as a first term for perturbation theory. And this is exactly what quantum chemists have been doing for the past 50 years or so. And they came up with a number of techniques. The first one, for example, is the Moeller-Plesset perturbation theory, where you start with Hartree-Fock and then you do perturbation using the usual quantum mechanical perturbation theory that you do use on that. We are not going to look at that in detail, but you would see this in, for example, MP2 or MP4. This would be MP is for Moeller-Plesset, and this perturbation theory on top of Hartree-Fock. They are pretty successful. Now the standard is probably, and more common, would be the configuration interaction, or CI. You may hear CI or full CI. In that case, we are looking for a solution which is actually a combination of multiple Slater determinants, essentially. I am not going to go into the details here, but this is just to tell you that Hartree-Fock is not the end of the road for those wave function approach to the solution of the Schrödinger equation. There are methods that go beyond that, and they're actually very, very successful. So there is also some historical aspect that, for example, when you do full CI or couple cluster or that kind of things, people used to say that these were this was the only ab initio approach as compared to DFT. We will have more than one opportunities to revisit this and discuss it. So before we depart on this, I'd like to give you a couple of exercises and we can discuss this. And I'd like to talk to you about maybe a couple of them. So, for example, for one electron, we can argue that Ex is equal to minus U. Well, that one is an easy one because, of course, the electron-electron interaction is Ex plus U. But the total, there is no electron-electron interaction in one electron. So therefore, Ex must be equal to minus U so that the sum of Ex and U equals to 0. That's pretty obvious. So think about it. Now, the more interesting point is number 2. The correlation energy is never positive. Okay? Why is it never positive? Well, the answer is actually, if you look back in the table a couple of slides ago, this was all negative. But the answer is actually pretty obvious if you follow the Hartree-Fock business, because remember, correlation is what we are missing due to the fact that we are not sampling all the possible wave functions, the trial wave function and the variational principle. We are only trying those wave functions that can be obtained by the product of single orbitals for independent orbitals. Therefore, at best, we can approach the solution, but we never get to the minimum of the expectation value of the Hamiltonian. If we do not get to the minimum of the expectation value, that means that we have to go lower. The lower part, we define it as the correlation energy. So therefore, the correlation energy is always negative. In other words, it always brings you lower in energy. Now, it can be 0, of course. When is it going to be 0? Well, it would be 0 when the electrons are indeed independent. And so the best solution for that is, for example, when you have only one electron. In that case, there is no problem with correlation, of course. So I hope that this screencast on Hartree-Fock, of course, this is not a Hartree-Fock course, but I'm trying to give you the most salient aspect of Hartree-Fock. And I hope this screencast has been enlightening to you. And we've actually spent quite a bit of time developing our intuition on all those operators and what's happening, what's complicated. And this is great because this is the perfect segue to the series of lectures that are going to follow this one, where we are going to now focus on the density and we are going to build the density functional theory. Thank you very much for your attention. Any question or comment, please use the YouTube comment and I will do my best to answer those questions and comment. Thank you.